Hi, my name is David Lacey, Chief Software Architect at Graphcore. I'd like to thank the organisers for inviting me to speak at this event. Today, I'm going to talk about the future of AI chips. Over the past few years, there's been an explosion of interest in specialised processors for the artificial intelligence and machine learning fields. This is understandable given the potential of the area and the heavy compute requirements of the applications, but it does lead you to think about where this current storm of innovation is going to go. In the future, what will your AI chip solutions look like? So what is going to make up the best chips going forward? You could look at the features of the chip itself. Over the past 40 to 50 years, the biggest gains in chip technology have been due to process improvements. However, the widely publicized end of Moore's law and the limits of Dennard scaling show that we cannot rely on similar gains just from process changes in the future. However, you could get clever with the digital or architectural features of chip design. Perhaps you get better use of the multipliers on the chip. The vast majority of work in AI is multiplying floating point numbers together. Or you could do more advanced multiplier design. Perhaps you could use alternative number representations or formats to get more effective use of your compute units. There's also interest in taking advantage of analog compute to get more power efficiency, though integration with a digital system is a major challenge here. So there are a few things you can do at the chip level, and we are doing many innovations in this area at Graphcore. There's also the system level to consider, that is, the system hosting the chips and the communication between the chips. Perhaps you can speed up the communication between chips with better networking infrastructure. You do have to pay in your power budget though. Or you could experiment with different modules and servers for deployment and bring in new cooling technologies to drive your chips harder. Again, there are a few things you can do at this level, the system level, but I believe the most important aspect of the best AI chips in the future is none of these things. There is one component that makes all the difference. I sincerely believe that the biggest factor in the effectiveness and success of AI chips will be its software stack. The most successful AI chip will be the one with the best software. Not only will the best software provide the most usable experience for developers, it will also be the one that can harness the potential of the underlying hardware. The key point here is that artificial intelligence and machine learning requires more from its software to get efficiency. What I'm going to do is explore what drives these requirements and how we are addressing them at Graphcore. One aspect that certainly stands out in AI is its applicability. It stands out amongst compute-intensive fields as the one that can be used in almost any area. Our experience at Graphcore has seen activity in healthcare with advanced deep learning and imaging. Finance is also active with the ability to get best-in-class accuracies and time to result in training, and inference in that area is the key to predicting market behaviours and trends. Automotive is also a steady area with the eventual road to fully autonomous Level 5 vehicles still a desired goal of most automotive manufacturers. Data center and consumer internet is very strong for general offering of machine intelligence as a service, and we support this through Azure Cloud, for example. However, the field doesn't just stand out in how it can be used. In artificial intelligence and machine learning, the compute itself is fundamentally different. It has different properties to other areas. This has a profound impact on how the chips and software need to work. There are many areas where things differ, but I'm going to call three out here. Firstly, AI and ML systems deal with probabilistic information. Secondly, they deal with data of very high dimensionality. And thirdly, they have entropy or randomness generated by the system itself. In addition to these extras, ML code has all the normal issues in software that we've been dealing with for many, many years in computer generally. Let's look at some of these compute differences in more detail. Modern AI and ML is all about dealing with uncertain information. The variables inside a model represent something uncertain, a probability distribution. This has a big effect on the kind of work the chip is doing. This is why floating point is so prevalent in machine learning and artificial intelligence, because the representation of the information is inexact and represents a range of possibilities. So you need both the detailed precision of fractional numbers and a wide dynamic range to cover the wide range of possibilities that occur. From a software point of view, this requires us to use a variety of floating point number techniques and also algorithms which are manipulating them in a probabilistic way. As well as being probabilistic, the data we're dealing with comes from a very high-dimensional space. When we talk about machine learning systems or artificial intelligence systems, they are handling the content of images, or sentences, or videos, or abstract concepts, which aren't just straight vectors of data like you get, for example, in graphics processing. They are naturally higher dimensional. Again, looking at it from a software point of view, this fundamentally changes the way we access data. If we have one-dimensional data or two-dimensional data, you can generally access data in big contiguous blocks. But once you get into higher numbers of dimensions, then the memory access becomes irregular, sparse, and generally random access. So many of the techniques we used in software and hardware, such as buffering, caching, and vectorization, don't really apply to this space. In addition to the previous points I've mentioned on why machine learning compute is fundamentally different, we also have to contend with the fact that machine learning compute deals with both big data, huge data sets from which to learn off, and big compute, a large number of computing operations per item of data being processed. This combination provides us with both the challenges you get in HPC compute and also the challenge you get in data analytics. So it provides a fundamentally different challenge to either of those problems. This is especially true when combined with the probabilistic, sparse, higher dimensional nature of the problems that I've previously mentioned. This brings us to the fundamental reason why I think the future of AI chips is about the future of the software stack. Artificial intelligence and machine learning computing is different. So, therefore, our software needs to do more than software does in some other areas. We need an advanced software stack that combines developer productivity, ease of use, and all those concerns, along with the need for efficiency for large-scale compute and flexibility, because this is a constantly evolving, innovative area. So, what kind of software features am I talking about? The first one I'm going to draw attention to is the need for software to control more of the lower level hardware details than has previously been the case in existing chips. We need software that can effectively analyze and understand our algorithms in such a way that it can control things like number representation and explicit memory movement that is specific for that algorithm. Aspects such as thread scheduling and lower level memory movement on current platforms is often deferred to the hardware at runtime. Scheduling and lower level memory movement on current platforms is often deferred to the hardware at runtime. So you have features such as instruction level parallelism or caching and so on that are trying to react to the software and what it is doing and make late decisions to make the overall system efficient. This actually works tremendously well. It is one of the big successes of computer science for general purpose compute. The developer doesn't have to worry too much about these low-level aspects, and it generally does a good job and gets 80 to 90% of the performance that you can possibly get out of that system. However, for AI machine learning, this doesn't work as well. The hardware reacting to the software at runtime and making late decisions ends up with inefficiency. This is actually related to the specific properties of machine learning and artificial intelligence mentioned previously. The probabilistic and higher order data structures make it harder to predict what's going to happen, so we need the software to do a job up front, whereas more information about the structure of the algorithm and the structure of the machine learning model that we're trying to execute. But analyzing to control these low-level hardware features is not the only analysis we need our software stack to do in this space. If you spend any time in machine learning or artificial intelligence, you will see many diagrams like this of compute graphs representing the data connections between different compute structures in a machine learning model. The software stack needs to analyze and optimize this compute graph heavily to be able to execute efficiently. The optimizations in this stack need to be tailored to create what is efficient on hardware, and the hardware should be receptive to that optimization. The idea that compute graph optimization analysis and optimization is so intrinsic to to the execution of algorithms in this field is the main reason that Graphcore is called Graphcore. It is because the concept of the compute graph is so central to everything that is being done. Finally, in general, this space requires more hardware-software co-design. That is when we design our software algorithms and the hardware at the same time. The reason we need more co-design is a similar reason to why software has to have more control over hardware execution. The type of algorithms we get in this space require upfront knowledge, and a greater has to have more control over hardware execution. The type of algorithms we get in this space require upfront knowledge and a greater degree of cooperation between hardware and software on what's going to happen and how to organize, for example, your memory locations or your thread scheduling. The best way you can do that is to make sure you design the hardware and software to work together from the outset. This is something that at Graphcore we've been very focused on right from the beginning, from when we had a blank piece of paper on which we were designing a chip. We started off by writing much more advanced application software models than you usually would for a new chip architecture. This is because we knew that the chip would be cooperating very closely with the software, so we had to have the software stack up and working from a very early stage. I'm going to change tack slightly now and talk about Graphcore. We are building products and solutions in hardware and software for the demands of today and tomorrow in machine learning and artificial intelligence. We design silicon specifically architected for the needs of ML and AI. These devices are called Intelligence Processing Units, or IPUs. IPUs are radically different from the historical architectures that have been on offer, the CPU and the GPU. In addition to our hardware solution, our software solution is provided by the popular software stack and development tools, of which I'll talk more about later. We then combine the hardware and software in platforms so they are plug and play for customers to simply install, deploy, and be thrilled. We have IPU server products we offer through third-party Tier 1 OEMs such as Dell and Inspur, and we also have rack-scale products that can ramp up into thousands of systems as suits the requirements. Graphcore are headquartered in Bristol in the UK, a historical home to semiconductor startups. We have R&D centres across the UK and an R&D centre in Oslo, Norway, which specialises in very high-speed networking amongst some other disciplines. We have sales and technical support offices and staff across China and across North America, Japan, Taiwan, and South Korea. Earlier this year, we released our new breakthrough product, the M2000. Unlike GPUs, which need a server plus expensive InfiniBand networking cards, the M2000 can be easily added into an existing data center with a dedicated AI-focused IPU fabric networking included inside the box. The M2000 IPU machine features a 4-way IPU engine with 4 of our new GC200 Mark II Colossus IPU processors, combined with an advanced airflow cooling system to fit in an easy-to-handle 1U chassis. This IPU engine is combined with an IPU fabric chip, allowing multiple M2000s to be added into the rack and racks of M2000 to be connected together to build large IPU pods. The chip inside this product is our second generation Colossus Mark II IPU processor, the GC200. Each GC200 processor has nearly 1,500 processor cores and runs nearly 9,000 independent parallel program threads with a proven multiple instruction, multiple data, or MIMD, processor architecture. Inside the processor, we've been able to fit 900 megabytes of an ultra high-speed RAM that runs at full speed of the machine. The chip has 250 teraflops of AI floating point capability, and we also support much more IEEE float 32-bit compute than any other processor. All of these advantages allow our Colossus Mark II based systems to deliver an incredible 8x speed up over our previous Mark I products. As I mentioned, the popular software stack is the stack we provide with this platform. This software stack works from standard ML frameworks, TensorFlow, PyTorch, etc. These are becoming reasonably standardized in the field, at least for deep learning type applications. Popper lowers the compute graphs and training loops provided by those frameworks, splitting the work amongst the parallel compute units, generating code and so on. And at each stage, the software will analyze and optimize in the way discussed earlier. The software stack is tightly integrated with the hardware design. Poplar has been developed from the beginning of the company completely in tandem with the IPU processor. From the very start, we designed the software and hardware together. Key to the kind of analysis that Poplar has to do is splitting the model across multiple chips and memories. This is the key to both the speed that the models can run and also how we can get extremely large models implemented on the chip. Recent progress in ML has been shown a drive towards larger and larger models. The recent language model from OpenAI, GPT-3 for example, contains 175 billion parameters. The actual components underneath the frameworks are a graph library, which allows you to specify the low-level computation graph of the device. This is very close to the hardware and is a fully flexible language that can implement any program. Although it is mostly compute graph-based, it includes the notion of sequential programs controlling the graph execution, which can fully support data-dependent control flow, etc. The compute graph and control program created in the graph library are then passed to a graph compiler, which does all the analysis, optimization, and code generation. Finally, the graph engine controls the execution of the algorithm on the IPU chips, interfaces it with the host processor, and optimizes data transfer into and out of the array of IPU chips. Details of all these components can be found on our website. The underlying structure of the graph library on our website. The underlying structure of the graph library allows people to build up common functions for machine learning. We provide many such functions in our own Poplar libraries. The libraries are built up in a way that allows the kind of software analysis I've previously talked about. Depending on the function, the library optimizes the exact level of parallelism and communication topology the hardware provides. One thing I haven't mentioned that is required for any software stack is a healthy developer ecosystem. You cannot underestimate the importance of comprehensive documentation and open sourcing of parts of the stack, and this is an area we're very passionate about. Now that we're acquainted with the Graphcore software solution, I'd like to talk about the way in which the software performs the advanced optimization and control I talked about earlier in the talk. Let's start with the communication inside the chip. We have 1,472 cores within the chip. Each of these has its own memory, and these need to pass information between them. Let's look how this happens. The computation graph is split into sequential layers of parallel compute sets that can run code in parallel across these cores. This gets loaded into a sequence of alternating compute and exchange steps, which follows the BSP or bulk synchronous parallel paradigm. These exchange steps are the ones that pass information between the cores. The key aspect of the way our software stack works is that the communication passed between the cores is known at compile time. So our graph compiler can schedule an extremely efficient communication schedule to do this communication. This is very different to how other processes work and relies on advanced software support. What about outside the chip? Again, this is an area where Poplar software stack exhibits more software control than in other systems. The M2000 system has off-chip DDR. However, there's no cache or anything in the hardware to automatically control at runtime the moving or buffering of data between the external streaming memory and the on-chip in-processor memory. It is all controlled in software based on the computation graph. And memory management is just one of the parts of the software stack where we optimize the hardware based on our advanced analysis in the software. It is key to our approach. In summary, I hope I've given here a reasonable overview of the importance of the software stack and how the best AI chips will be the ones with the best software. Now we believe that Graphcore is going to provide those chips. We are a software company now as much as we are a hardware company, and we truly believe that this is the way forward. Thank you very much for listening. If you're interested in any of the products or more details of the software that I've talked about in this talk, then feel free to visit our website.